Hello everyone, this is Dr. Bread. Today we'll explore blackbody radiation and the quantum revolution. Today, we're going to tell one of the most exciting stories in the history of physics. The protagonist of this story is a seemingly ordinary phenomenon, blackbody radiation. This ordinary phenomenon, however, triggered a revolutionary wave in the early 20th century. It destroyed the classical physics framework that had lasted for 300 years. And the second cloud directly led to the birth and development of quantum mechanics. Ultimately, it led to the birth of transistors, lasers, and quantum computers. It's safe to say that without blackbody radiation research, there would be no modern technological civilization. Even more interesting, the revolution's initiator, Planck himself, was essentially forced into it out of desperation. Throughout his entire life, he felt uneasy about his quantum hypothesis. So what exactly happened? Let's start from the beginning. First, we need to understand what the concept of a black body is. In daily life, the objects we see all have their own colors. A red apple looks red because it only reflects red light. A white wall looks white because it reflects all colors of light. And black coal looks black because it absorbs almost all light. So is there an object that can absorb all light that shines on it without any reflection? This is what physicists define as a black body, a perfect absorber. A perfect black body doesn't exist in reality, but there are clever ways to approximate it. Imagine a hollow metal sphere with a small hole in its wall. When light enters through the hole, it will reflect repeatedly off the inner walls. With each reflection, a portion of the light is absorbed, making it very difficult for it to eventually escape. Therefore, from the outside, this small hole looks just like a perfect black body. This is the standard laboratory method for creating a black body, using a cavity. So why is the black body so important? The key lies in its properties. When you heat a black body, it emits thermal radiation. This thermal radiation has a magical property. It depends only on temperature. It is completely independent of the material the black body is made from. For example, if you make a black body cavity from iron and heat it to 1,000 degrees, and then you make an identical black body from copper, also heated to 1,000 degrees. Even though iron and copper are completely different materials, their radiation spectra will be identical. This discovery was made by the German physicist Kirchhoff, first proposed in 1859, and is known as Kirchhoff's law of thermal radiation. Kirchhoff discovered that for any object in thermal equilibrium, the ratio of its emissive power to its absorptive power is a universal function. This function depends only on the radiation's wavelengths and the temperature, independent of the material's properties. Why is this discovery so important? Because it implies the existence of a universal law. Blackbody radiation reveals a fundamental law of nature. It describes the fundamental relationship between energy, temperature, and electromagnetic radiation. It is one of the fundamental laws of the universe and must be deeply understood. Kirchhoff realized the importance of this and challenged the physicists of his time. To find the exact mathematical form of this universal function. This challenge seemed simple. Just measure the spectral data and find a formula to fit it. But no one expected that this very problem would push classical physics to the brink of collapse. Before discussing the crisis, we must first understand the mindset of physicists in the late 19th century. It was an era of confidence. Newtonian mechanics had ruled physics for centuries. Maxwell, in the 1860s, had established his grand theory of electromagnetism, successfully unifying electricity, magnetism, and light, and predicting the existence of electromagnetic waves. By the 1890s, many physicists believed physics was essentially complete. Lord Kelvin famously said the edifice of physics was complete, and future work just required minor patching up. He also said that in the bright, clear sky of physics, there were only two small clouds. One was the Michelson-Morley ether drift experiment, and the other was our topic for today, blackbody radiation theory. Kelvin thought they were just asterisk, small asterisk clouds, but history proved he was very, very wrong. These two clouds would soon trigger two massive storms that would completely destroy the edifice of classical physics. The first cloud led to Einstein's theory of relativity. Now let's focus on that second cloud, the blackbody radiation problem. In the late 19th century, the German physicist Wilhelm Wien proposed a law. Wien was an excellent experimental physicist. He carefully measured the spectra of blackbody radiation at different temperatures. He discovered that as the temperature increases, the peak of the radiation energy moves towards shorter wavelengths. You may have seen this phenomenon in daily life, for example when heating a piece of iron. At first there's no visible change, but it's actually already emitting infrared radiation, which is invisible to the naked eye. When the temperature rises to about 500 degrees Celsius, the iron block begins to emit a dark red glow. As the temperature rises further, it will turn bright red, orange, yellow, and finally white hot. This is a clear example of the radiation peak moving toward shorter wavelengths as the temperature increases. Based on these observations, Wien proposed an empirical formula to describe the blackbody radiation spectrum. This formula was very successful in describing high-frequency, short-wavelength radiation, fitting the experimental data perfectly. But problems soon appeared. By the late 1890s, German scientists had improved their experimental techniques, allowing them to precisely measure low-frequency, long-wavelength radiation. They discovered that in the low-frequency region, Wien's law failed completely. The experimentally measured intensity was far greater than the prediction from Wien's law. This greatly puzzled physicists. Wien's law, a formula that was so perfect in the high-frequency region, why did it fail in the low-frequency region? Clearly, Wien's law was only an approximation. It was not the universal function Kirchhoff was looking for. So could we derive the correct formula from the first principles of classical physics? At this very moment, some physicists decided to start from the most basic principles of thermodynamics and electromagnetism. Their idea was that the inside of the blackbody cavity was filled with electromagnetic waves. These electromagnetic waves form standing waves inside the cavity. Just as a guitar string can vibrate at different frequencies, this cavity also supports countless different modes of vibration. According to classical statistical mechanics, at thermal equilibrium, energy should be distributed equally among every possible mode of vibration. This average energy depends only on the temperature. This is a core idea of classical physics known as the equipartition theorem. The British physicist Lord Rayleigh and later Sir James Jeans derived a new formula based on this. Interestingly, this Rayleigh-Jeans Law fit the experimental data perfectly in the low-frequency region. This seemed to validate the correctness of classical theory, suggesting the first principles approach was right. But there was an asterisk, huge asterisk. But when physicists looked at the high-frequency region, the problem is the number of possible vibration modes in the cavity increases rapidly with the asterisk square asterisk of the frequency. Let's think about what this means. If there are more and more modes at higher frequencies, and each asterisk mode gets the same average energy, then what should the total radiation energy be? The answer is infinity. That's right, you heard me. According to the unshakable laws of classical physics, any black body at any temperature should instantly emit an infinite amount of energy. And this infinite energy would be concentrated mainly in the high-frequency regions, ultraviolet light, X-rays, and even gamma rays. This is, of course, completely absurd. In reality, you, me, and the desk in front of you are not emitting infinite energy. In fact, the experimental data clearly shows that a black body's radiation intensity quickly decays to zero in the high-frequency region. This catastrophic prediction was given a very fitting name, the Ultraviolet Catastrophe, because, according to classical theory, all the energy would catastrophically flood into the high-frequency or ultraviolet region. The ultraviolet catastrophe wasn't a small problem. It wasn't something patching up could fix. It was a complete fundamental failure of classical physics. It showed clear as day that our proud classical physics completely failed when trying to describe the microscopic world. The entire physics community fell into a state of deep confusion and anxiety. Either the experiments were wrong or the theory was wrong. But the experiments had been repeatedly verified by different scientists and were irrefutable. So could it really be that the classical physics theories we believed in so deeply, the ones we held as gospel, were fundamentally wrong? At this critical moment, a German physicist stepped forward. He was Max Planck, a scientist known for being conservative and rigorous. Thank you for watching. This is Dr. Bread. See you next time.